Log on, tune in, find out. Another good idea from Cambridge.
The term Yang-Baxter maps, for those probably that they don't know, refers to maps in general. We're referring to finite dimensional mappings, integrable probably, etc. But essentially, by the term Yang-Baxter maps, there are actually difference equations, partial difference equations, and I'm going to show you how this can be done. Actually, why this is so. Okay, some terminology and definitions. Now, the name came after some longer names, actually. There is an article by Skyanin, 1988, that apparently Drinfeld didn't know about. And in there, Skyanin presented some, what now we call Yang-Baxter maps, as classical limits of solutions of the quantum Yang-Baxter equation. And then Drinfeld in 1990, I think, posed the problem of the so-called set theoretic solutions for the quantum Yang-Baxter equation. Meanwhile, there is work by Weinstein and Xu, on classical solutions of the quantum Yang-Baxter equations. All of them are the same, that is Yang-Baxter maps. And finally, Sasha Veselov coined the term, the short-term Yang-Baxter map, which is short and easy to use. Now, what is a Yang-Baxter map? Let's consider any set. It's a combinatorial, actually, thing at the beginning, any set X, and then a map from the Cartesian product of X times X to itself. There is an equation associated to this R that is an equation for mappings on the triple Cartesian product. So you have X times X times X here. Now, what is the meaning of R12, R13, and R23? For those that don't know from quantum Yang-Baxter equation, although this is more or less known, is that we act on 3 copies of X. So R12 means that R, essentially R, acts on the first and second component as R itself, and then the third stays unchanged. Then 1, 3, the result of this, you apply R13, then you act on the first and third component, the second remains the same, and 2, 3, the second and third. So this is this equation that says that this composition of mappings in X times X times X, the triple Cartesian product, is equal from one side and the other. Okay? So this about the definition. Now, why this is a partial difference equation? Now, one looks at R as going from X and Y to U and V, and X and Y are assigned at edges of quadrilaterals. Now, I haven't written down this property, but the usual, I mean, all Yang-Baxter maps we consider are involutions. So R squared is the identity, which means from this point of view, as a mapping, the dynamics is trivial. However, if we couple these mappings in the following way, So here we have U1, V1. Here we would have U2, V2, U3, V3. Then we evolve this pattern of initial conditions here that could be given in the infinite zigzag line here, or with periodic conditions or some other condition, boundary conditions. And then we move to the upper one, and so on. So actually, this is the coupling. And you see, it's a non-trivial coupling, because then you compose U1 with V2. U1 from this side and V2 from the other side. So it's a non-trivial coupling. And actually, these are the so-called transfer maps introduced by Vassilios. And from this point of view, this is a partial difference equation. Okay. So essentially, we're talking about partial difference equations that we all know. Now, some other properties that are important. Usually what we are dealing with are rational maps. They have rational form, so X is not only a set. By the way, there is also an amount of work on just finite sets, Yang-Baxter maps, solutions of this equation for on finite sets. And there is a lot, a big connection with algebraic structures, actually. Now, we are considering when we fix one of the original X or Y inputs, we think of U as a function of the other, U as a function of X, V as a function of Y, and then we want these two functions to be bijective, and in the rational case, rational maps. In this case, we call this map quadrirational. This is a term given by Adler-Bubenko and Souris in some classification they did. We are going to refer to that later. There are other, actually, in some other terminology, this is called the non-degeneracy condition. So if you don't have this condition, the map is called degenerate or non-quadrirational. If you have it, non-degenerate or quadrirational. Now, on top of that, it's interesting to consider, and actually the ones, the Yang-Baxter maps that are associated to integrable difference equations are associated with parameters on the lattice. So alpha and beta are parameters that are assigned on the edges as actually the fields I put down there. Well, you are going to say that, of course, you can incorporate alpha and beta to X. So your original set is going to be extended. So you would have for X times the set where alpha and beta live. You can do this, but well, it's interesting to have them apart and see how they correspond, as we are going to see later, to Casimir's, actually. So it's easy to have them apart, and their evolution actually is the identity map. So if you have here alpha and beta, then here you are going to have alpha again and beta, and so on. So all edges parallel to this one is assigned with alpha, and the other edges with beta. Now, there was a classification by Adler-Bubenko and Souris for X, the CP1 space. So they considered quadrilateral Yang-Baxter maps on CP1, and they classified them. Actually, the classification goes like the classification they gave for this multidimensional difference equations, multidimensional consistent partial difference equations. And it goes with a nice geometric interpretation. The classification ends up with 5 representatives. The top one, as in the Q4, well, it's not exactly the analog, but the top one is the most general, and then with the limits and special cases, you go down to the first one. And I say it's not the analogon of Q4 because it's not elliptic. It does not involve elliptic functions in the parameters there. Now, this classification can be derived, actually the representatives of this classification can be derived from equations that are consistent around the cube by symmetry reductions. Tassos Togas talked actually probably a month ago or something, some weeks ago, about this, how from the consistent around the cube partial difference equations, by considering Lie point symmetries, you go to some other variables on that are assigned on the edges, and you get that picture there. You get coupled Yang-Baxter maps that are equivalent to your original partial difference equation. And it's important to note that almost all of the 5 mappings in the classification of Adler-Boubenko and Souris, you can derive them from the discrete potential KdV equation that was derived from direct linearization of Capel, Frank Nijhoff, and Reinhard Quispel, by considering not only the KdV equation itself on the Z2 lattice, but higher consistent analogs, multidimensional consistent extensions in Z3 and Z4. So you use different symmetries, different symmetry reductions, plus you go up to dimensions 3 and 4 in order to derive all 5 maps, Yang-Baxter maps, that was in the classification of Adler-Boubenko and Souris. Now, for the integrability of these maps, of course, and the associated partial difference equation, we all know that Lax matrices play the central role. Although Sasa-Veselov for transfer maps proved that the transfer maps derived from that picture there, more or less, they commute. So you have a family of commuting maps, but in order to get complete integrability of your system, you rather try to find Lax matrices and then from the monodromy matrix derive the first integrals, show that they are in revolution and so on. So there is an obvious actually definition of a Lax pair for a Yang-Baxter map, and here L is a matrix or an operator sitting on the edges. So Lx alpha sits on the edge where you have assigned x and alpha, yb, beta, and so on. And if you have this equation, you have this equation which is valid if U and V are given by the map, then you say that L is a Lax matrix for this Yang-Baxter map. Now, in their definition, they actually asked for one direction. If you have U and V given by the map implies this relation. However, it's better, of course, if you have, and usually this is what we're looking for, a Lax matrix where this relation actually implies the equation, the original equation for the map. Now there is a proposition that, you see, this relation gives you the map. You know nothing yet about, yeah.
Isn't it usually so that the equation implies the Lax representation, so the other way around?
I would, well, it depends on the definition, of course. If we agree that a Lax pair is when this is equivalent to that, the equation is equivalent to the equation there, then you call this a Lax matrix. But what you said, if the compatibility implies the equation, you mean?
Oh, I don't know.
Well, the way it's written there is, if U and V are given by the map,
yeah,
and you put this x, y, and U and V there, then this is true. So the map implies that the product of these matrices is the same.
Yeah, that's what
Okay.
yeah.
But usually you would like to have even in the stronger sense.
But you usually don't have that, do you?
Well, for KDV at least, and yeah.
Oh, for KDV, yeah, but that's because, well.
Yeah, but,
First thing is one.
okay, yeah. But I have some cases where you don't have this. Okay, you don't have the strong sense, the equivalent there. Okay, now, with respect to this proposition, then, of course, when you have something like this, you have a Lax pair for your map, you are asking the question if you can read in terms of this matrix the Yang-Baxter property of this map. And this proposition tells you that if you have this property for a matrix A, then you know that R has the Yang-Baxter property. And the proof actually uses just associativity of matrix product. Okay. Now, what is our aim for this consideration of Lax pairs? We pose the following problem: to find the Yang-Baxter maps that come from 2 by 2 Lax matrices and are first-degree matrix polynomials with respect to the spectral parameter. Now, there is work by Resetichen and Vassilios, and actually in Souris and Vassilios that they gave the definition of Lax matrices. They had a lot of examples there. But we posed this question to try with as much as elementary means to come up to Yang-Baxter maps that have this kind of Lax pairs. So from what you are going to see here, of course, you have the idea that all of these things are connected with Backlund transformations and dressing, actually the dressing method. And in there you have, we're going to see actually afterwards, the theory of Poisson-Lie groups, and there is work by especially Semerov-Kershansky on this approach. However, we took the most elementary approach to look, to consider this type of matrix. So zeta here is the spectral parameter, and try to see if we can get Yang-Baxter maps that have this as a Lax matrix. So what this consideration boils down to this matrix equation, actually. So you have here everything you see with capital letters are, for the time being, 2 by 2 matrices. So for considerations you are going to see later, actually, this B, we took it as constant, the same. So now you change, you have X and Y that are 2 by 2 matrices. So this will be the fields that I put before at the edges. And then we update them with U and V, okay, to the opposite edges. Okay? So you're going to see if this equation, so we are at the level of actually the other way around. I have a matrix, and I want to see if this can be considered as Lax matrix for a Yang-Baxter map. Okay? Of course, you are going to say that here is a solution. You expected that, of course, so this is kind of trivial. Now, the proposition is the following. As I told you, it's just pure linear algebra, so everything here has to do with matrices. So what you get is the following. Define U and V as function of X and Y by these two formulas there, where P1 and P2 are given by X, Y, B, etc. The matrix is here. And now the coefficients, F1 of X and F2 of X, actually turns out to be the Casimirs. So the approach, as I told you, was elementary to try to ignore the big idea behind that, which is Poisson structure, and actually the Sklein bracket will appear later. So you just try to solve the previous equation, okay? For zeta is the spectral parameter, so you get some equations for matrix equations, and you end up with this solution where F's are the coefficients of the, well, almost characteristic polynomial. It's the determinant of A minus zeta B, okay, and actually 2 of A is the determinant of B, is constant because we fixed B, and the other F1 and F0 actually is determinant of A. It's missing there, it's determinant of A. Okay? Now, how difficult is to obtain this solution? You just use Cayley-Hamilton theorem. Now, what is the idea? First of all, and how you actually the hard part, say, is to come up with considering the determinant of this and see that you have this. It's reasonable to ask for Fi to be invariant on parallel edges, actually. Now, how you prove that this is a solution? From your equation.
Sorry, Vassilios.
Yeah.
So this can be done for arbitrary constant matrix B?
Yes. Well, okay. First of all, B has to be invertible. And also you have conditions. Yeah, because I have B minus 1. Yeah.
In a lot of cases where you have a Lax representation, is it actually the case that B is actually not invertible?
We're going to see what is going on. Yeah, correct. Actually, you have also some conditions. This is the generic, say, with x, y generic, because you might have singularities like the determinant of u minus x to be 0. You try to avoid this kind of initial conditions. Okay, we are in the birational case, so these are reasonable conditions to impose. But the thing is that what goes with the proof is the following. You are trying to solve for u and v in terms of x and y. Now there is the so-called associated map when you solve for u and y in terms of x and v. And this is one of the keys for the proof. Now, these equations can be solved for u and y in terms of v and x because they are first-degree equations for these matrices. However, for the other way around is second degree. So first, you solve for u and y in terms of x and v, and you realize that actually you have to have this condition that the fi's of x have to be the same as the fi's of u, and the fi's of y the same as the fi's of v. So somehow the Casimirs are already hidden. I mean, you derive something with respect to the Casimirs, that they have to be the same on these two and the other two edges. Okay? And once you realize this, then you use Cayley-Hamilton theorem. And you drop the degree. I said that it's of degree 2, the equation for u or v. And you use the Cayley-Hamilton theorem, so you have already a relation for u squared as a polynomial equation with quadratic, and then you drop down the degree to 1, and then you solve. So this is how the proof goes, actually. And there is actually a way to find, to derive a solution for n by n matrices. Because there you have n degree, the characteristic polynomial for u, well, it's not exactly the characteristic polynomial, but it's this with zeta b. Essentially, it's the characteristic polynomial if b is invertible, okay? Then you drop down the degree from n to 1 using the equation, because the equation is of second degree, and you get, well, of course, you have some finite recurrence for coefficients, etc. There, it's not as easy as this one to write it down. Okay. Now, what do you do with this solution, or towards the integrability of these mappings? So you have a non-parametric big map, because here you have from GL2 to x is GL2 here. So you have 4 components. Okay. Now you consider the Skleinin bracket. So the Skleinin bracket is given by this Russian formula, and this is actually tensor product with this comma means Poisson brackets, okay, between the elements of L zeta and L eta. This is the antisymmetric matrix. This is the Poisson structure matrix, and finally you get. Sorry. Here, it works for GLN, but here is GL2. Yeah. Okay. So finally, what you get actually is that B. That's why you take B to be constant. You could alternate though. You could take for B two values to go between two values, but this is a generalization. We fixed B because the elements of B are Casimirs of this bracket. So finally, what you actually have are brackets for the entries of the first matrix, this matrix here, where actually your fields are. Now, first of all, as I said, fix B. So you already are on a Poisson submanifold. And then you have two Casimir functions. One of them, once you fix B, F2 is already the determinant of B. Okay? And so you now have two Casimir functions for this bracket. And by extending this Poisson bracket on the product of this not yet symplectic leaf, but this Poisson submanifold, you get that the Yang-Baxter map, the map we derived before as solution of the matrix equation is a Poisson map with respect to this Poisson structure. And actually one can prove that it's a Yang-Baxter map. So satisfies this L satisfies the condition given at the beginning as a 3 factorization. Okay? We use the proposition that was written down by Vassilios. Now, what one can do next with respect to this matrix B, and here we are approaching right now your question. Okay, first of all, we can normalize B using conjugation by an invertible matrix, and of course this goes for the matrix equation to get the mapping, but also it's compatible with the Yang-Baxter equation. Okay, one has to sometimes one could say if B is invertible, let's take it just identity. This is not the case because you cannot always conjugate in such a way as to respect the Yang-Baxter property as well. Okay? So by this conjugation here, you see that B can be fixed to one of the Jordan normal forms. If you look at even the real case, you can consider this one as well. But in principle, you have two different eigenvalues, one double and still diagonalizable, and one with one Jordan block. Okay? Now, take the Casimir. What you can do now is consider the Casimirs, and from the two Casimirs, and then, okay, you have here the Poisson brackets, and then if you consider these two Casimirs, and you put fixed values that go with the edges there, you can solve for two of the, you can reduce, essentially, okay? So you go down, for instance, here is a case where B is identity here, and then you have two fields, A1 and A2 on each edge. And on top of that, you have C1 and C2 as two parameters. You have two parameters on each edge. Okay? And you write down a parametric Yang-Baxter map. Well, C2 actually is a projective space because of singularities. It's birational. It's quadrirational, actually. And here is the symplectic structure that you read off from the Poisson matrix. It's easy. Once you fix B's, then in the Poisson matrix you have only the A's. Okay. So now this actually is a known map, is used as for background transformation, etc. Is associated to probably some dimer model It's in the work of Sklianin, actually, previous work of Sklianin, of Backlund transformations and so on. Now, what is interesting here is to consider cases where your matrix B can become singular. So you start with this case here, 1 and epsilon, the diagonal case, and consider again the Casimirs. For this case, write down the map, and you can take the limit. Well, you have to choose which way to solve using the Casimirs. I haven't put that down. And then in a limit, when epsilon goes to 0, you end up with this map. Now, I put the name Adler-Yamilov because they, in an article on Otto Backlund transformations that were related to Schrödinger systems, Landau-Lifshitz type of systems, etc., they write this kind of maps, actually not as Yang-Baxter maps, but as a two-field partial difference equations. And in this form, you can see they can be written in the form of a Yang-Baxter map. So if you wish, you get from this business here, in this limit, the map that is associated to some Backlund transformations of actually superposition principles of Backlund transformations of the Schrödinger system. Just from the Sklianin bracket, you get these are actually, you are already on the symplectic leaves, and this is a symplectic map. Sorry. No, yeah, I put it here. It's the canonical one. Yeah, sorry. Now, the last slide, actually. Here we come back to the beginning at the KdV, discrete KdV equation. So take B to be of this form with one Jordan block. Double eigenvalue, so double eigenvalue with one Jordan block. Then, again, you go through the reduction using the Casimirs. You take the limit when epsilon goes to 0. You end up with this map. So it's a two-field map, again, x1, x2, y1, y2 to u1, u2, v1, v2. Well, the bars is because we took the limit before it was with the epsilon side. And you have the symplectic form, etc. Now, how this goes down to KdV, actually. And probably Tassos Tongas showed you this, and even a more general situation where you have these lifts of Q4 in general equation. So because of these two equations, U2 is the Y2 and V1 the X1, if at the beginning, what is the thing? X2 equals Y1, then you have that U1 equals V2, and then you have just one field, and this one field, call it F, where you change a little bit the signs here in order to have it exactly in this form. So you have to go all this the way around, I mean, from to do the classification to get this Jordan block, and then in the limit to get the lift of KdV, actually. Now, there is work also that is going on 3 by 3 where you have to do some more tricks to get the Boussinesq equivalent, the Boussinesq analog. There, you have 3 Casimirs, but you have 9 fields. So 3 Casimirs, you have 6 fields on each edge. And the thing is how to go down to 4, actually. And there you use a special relation between the values of the Casimirs. You don't have, you cannot stay with the arbitrary values on the Casimirs. They should be related. And you get Yang-Baxter maps related to Boussinesq system. So that's all. Thank you.
By taking the first degree lax pairs, if you consider higher degree lax pairs, can you make sense of some of these constructions in terms of correspondences?
You don't have necessarily correspondences. I mean, here you can have correspondence when you put your initial value problem in a different way as well. So the correspondence goes, well, you are going to say that probably with the fields you have in there, probably some of the equations could be, when you solve for them, could be some plus minus signs for square roots, etc. No, I haven't tried yet. There is, one should, take into account some higher degree polynomials. However, I think that one should work with the most basic ones, because then, well, actually there is a conjecture of Sklianin that, in higher degree polynomial can be factorized in elementary ones.
How is it with correspondences on the Yang-Baxter map level? Because the Yang-Baxter map is kind of, by definition,
No. When you put the same thing as with equations, if you, well, let me put it this way here. So if you give me data here and there, but then I consider periodicity this way, then you get a correspondence.
Okay, in this way,
Yeah.
Further questions? Let's thank Vassilios again.